Thanks for the introduction. I'm very glad to be here to share some of the work we did in the last 1 or 2 years. Actually, I came to this event multiple years. Every time, I hope I can bring some new story, what kind of new system, especially the emerging system can get the benefit from RDMA networks. Hopefully this time with TensorFlow, you'll get some new story from my talk. So I believe a lot of our talks already discussed why deep learning these days is becoming so hot, right? So there are the main reason behind this actually because there are 3 different kind of pillars trying to speed the development of deep learning area. So first one is definitely from the model or algorithms. A lot of people trying to propose new or advanced models to get more accurate results. And then second thing is about data, especially a lot of big data sets available on the websites or on the community, so you can download and train with it. And the third most important thing is about computational storage capabilities. This is more related with our this community, right? Especially with GPU or high-performance networks, we are able to deliver fairly good performance, and then we can train this data in a very fast manner. So there are a lot of applications you can actually develop with deep learning technologies, right? So this one is just from FLICKR, one of the example how you can automatically tag tens of thousands of your images and then give you some information of each of these images means what, right? For instance, they can automatically generate the tags for sunset or water, snow, so you don't have to do it by manually. The machine will automatically do that for you. But behind it is actually using deep learning, big data, as well as HPC technologies for that. So, but because of this deep learning becomes so hard, right? A lot of people trying to work in this area, and we'll see that a lot of deep learning stacks are available in the community as well. Here, just a very short list of them. Many others actually not included in the list. So if you look at the trends of these deep learning stacks, you will see that the Google TensorFlow, as well as PyTorch, these 2 frameworks become pretty widely adopted by many industry as well as academia institutions. So in this talk, we are mainly focused on the TensorFlow. And a lot of us are working on the convergence between among HPC, deep learning, and big data. This is just a high-level overview of how different areas can benefit. Go inside, we really take a look at what these people are currently doing on each of these domains. We will see that a lot of concrete works have been happening under each of these subdomains. For instance, for deep learning side, a lot of people trying to develop new models, new algorithms, also new runtime or libraries, right, or frameworks, including TensorFlow or CNTK or Caffe, those things. And then for big data area, like people trying to develop a lot of advanced or well-designed distributed computing systems or distributed storage systems from across different layers. For instance, Hadoop, Spark, or Yarn, or HDFS, OrangeFS, those kind of things. And then for HPC, we are trying to deliver high performance, so that we are trying to deliver a lot of high performance communication or computation libraries. For instance, like RDMA libraries, GPU direct RDMA libraries, and as well as some CodeRDN or MKL libraries for that. So now the question is how we can really make these 3 domains. We get the idea or get the advanced knowledge from each of these domains, and then we can put together and then build up some very advanced systems to help deep learning applications. So with this, I put together an outline. So we are trying of TensorFlow and the gRPC first, and then after that, we'll give you some concrete examples how we can actually accelerate TensorFlow as well as gRPC with RDMA.
We're going to switch this out really quick.
Okay, sure.
That might just got them mixed up. Okay. All right, see ya.
Yes. So another thing is we also want to highlight is that in order to show the benefits of these designs, you need good benchmarks. we are trying to discuss what kind of benchmarks we can develop and whether the current or existing benchmarks is sufficient or not. And then we'll show you some example numbers we evaluate across different models. So this is just a very high-level overview of TensorFlow. There's multiple layers. You can program with TensorFlow with their C API, Python, or C++, those kind of interface. And then internally they have different kind of kernel implementations for very standard operations for deep learning trainings. And then underneath they have different kind of channels you can utilize with different kind of hardware. For instance, you can use RPC, you can use direct RDMA or MPI. And then you can use CPU for training, GPU for training, or some other kind of ASIC-based deep learning devices as well. So, but internally, if you look from communication perspective, by default, TensorFlow is trying to use a protocol called gRPC. This was developed by Google RPC protocol. So Google RPC protocol not only used just for TensorFlow, it's being utilized by many other industry applications as well. So this is just to give you an overview of how gRPC works. So typically you have a gRPC server and then you have gRPC client. It can be written with Ruby or Python or C++, whatever. They support different languages. And then through protocol buffer protocol, you are able to communicate between client and the server. So if you put gRPC and the TensorFlow together, this is how this very simple one parameter server and then one worker process, how they work together basically, right? So for worker, you are trying to train your model and then you get some parameters, and then through gRPC protocol, you are able to update the models in states safely in the parameter server process, and then after one round of training, you are able to get the latest model parameters as well through gRPC code. So not only for gRPC, because these days people are trying to develop some kind of a new enhanced communication channel for TensorFlow as well. So there's a new trend called gRPC plus X, like in HPC we call MPI plus X. So in TensorFlow area, people are trying to use gRPC plus X as well. For X can be MPI, can be verbs, or can be anything else. So because in our group, we have done a lot of studies to try to optimize distributed computing frameworks, no matter Hadoop, Spark, or TensorFlow. We are trying to utilize RDMA to accelerate the communicator engine as well as the pipeline for that. So that's why we are trying to see that whether we are able to do similar things for TensorFlow. This is one thing. Second thing is we are also trying to see whether if we just accelerate gRPC runtime, whether TensorFlow can be benefit or not. And then what kind of benefits we can achieve through our design. So now let's take a look what kind of things we can do with gRPC in the TensorFlow framework. So this is the standard way how, or default approach how you communicate between one worker and the one parameter server in TensorFlow, okay? Let's say this process is a TensorFlow parameter server, and then this process is a TensorFlow worker, one worker, just one worker, one parameter server example. And then this worker is trying to say that, okay, let me get the latest parameter from the parameter server. So then this guy will construct the gRPC request and then send this request through send message primitive and then come to the TensorFlow parameter server side. And then parameter server actually has internally has a table which save all those kind of model parameters. And then with this request, they're able to get the requested parameter. And then they were trying to serialize this parameter or those information to a tensor buffer. And then they were, through the gRPC response, they will send this tensor back to the client, like a worker, okay? So this is a default approach how you can communicate between worker and the parameter server through gRPC protocol. So internally, the tensor transmission is utilizing the IO-fake structures. So like I said, you can use gRPC to do that, just like I mentioned in the earlier slides. You can also use gRPC verbs. Basically means you are using gRPC just for control messages or administrative tasks. But you can use verbs to directly communicate between worker and the parameter servers to transfer those tensors. This is one way. The other way, you can also use gRPC plus MPI similarly, but this gRPC plus MPI is not like the or-reduce-based approach, okay? That one is from the Hollow World approach, which use MPI for distributed TensorFlow, is based on reduced tree kind of approach, not a primary server. So in this talk, we are mostly focused on these two, gRPC plus verbs, gRPC plus MPI. They are still utilizing the primary server architecture, but they are trying to use different kind of approaches to accelerate communication. So, like I said earlier, internally, because gRPC trying to utilize IOV structure to serialize or to transfer all those tensor information between worker and the primary servers. So we did a very detailed profiling, trying to show that what kind of IOV structures looks like, or under different kind of different model trainings, what kind of IOV structure pattern will be get generated during your training processes. Actually, we observed some kind of interesting phenomena here. So broadly, we divide into three kind of distribution. One is uniform distribution. For some cases, you will see a lot of small IOV structures get linked together and then send it out. Or you have a little bit different patterns, just small, medium, but still uniform, right? And then you have a lot of large one, maybe. That's also possible. And then the other case is very random. It doesn't know any pattern. Basically, you can say, right? You see some small one, medium one, small one, and suddenly the very big one. And then sometimes we will see a very big one, and there's only 1, 2 bytes or 3 bytes at the end. But they constructed like two IOV structures. And then there's also some kind of pattern we call skewed pattern. There's a like maybe hundreds of small ones, and then suddenly there's one big, okay? Or a lot of big one at the end of the small one. So we broadly divide into these three different kind of distributions, but if we can provide it more, we probably can describe these patterns in a more accurate manner. But anyway, the idea here is that because of this kind of patterns happening internally for the tensor transfers, so we need to design our communication engine in a very adaptive manner so that we are able to provide best performance under these different kind of communication scenarios, right? This also brings some kind of challenges to our designs or to our RDMA-based designs because we all know that for some small message, we should use this kind of protocol. For some large message, we should use other protocols. So then what our approach is, we call adaptive RDMA-gRPC. Basically, we still want to keep gRPC runtime. At least the API is not, we don't want to change any API or the semantics of gRPC so that you don't have to use gRPC plus X. We can drop X, we directly use a unified runtime with RDMA. Basically gRPC with RDMA so that you can run TensorFlow directly, right? But actually this design not only for TensorFlow, as long as you use gRPC in your system, you should be able to get the benefit from our design, I guess. So the high level idea is still like this. So this is the worker, and then this is the primary server, right? Earlier we said there is some kind of socket-based send message or receive message API get called in gRPC layer, but we designed some adaptive RDMA protocol over here so that we can use some adaptive protocols to send a small message, big message, and medium messages together. And then we're also trying to do some kind of message pipelining and coalescing. For instance, if we see a lot of small ones, we are trying to combine them and then send ones. If you see a very big one, then we should be able to do some kind of chunking-based pipelining. But all these kind of things we can hide in the gRPC runtime so that you can get a good performance when you trying to transfer different kind of tensor patterns. Of course, we also optimize a lot of serialization and deserialization code paths so that we can achieve zero copy-based transmission between the worker and also its primary server. So this is what we did for gRPC runtime, because TensorFlow will utilize gRPC directly, right? Because we don't change any API, we don't change any semantics, so TensorFlow can run with our library directly. You just have to link our library, and then it will run. So later on, we are trying to see that, okay, we have this design. Now let's see how we can show the performance benefits or what kind of experiments we can do. So with that, we actually did some survey, okay, what kind of benchmarks are available or what kind of models and data sets we can download from the community. We see that a lot of them are available, like I mentioned earlier. You have a lot of models like NotNet, VGG, ALEXNet, GOOGLENET, ResNet 50, 150, and then Inception, V2, V3, V4, those kind of things. And then you can download different kind of data sets as well. But the problem is, what we see is that all these kind of benchmarks, they actually designed from deep learning perspective or deep learning scientist perspective, So they are more trying to see whether the model is accurate or my data set is accurate, so your training is can converging at the end, those kind of things. It's not from system researchers' angle, actually. So that's why we'll see that in order to train a good model to get more than 80% or 90% accuracy, you have to train more than 1 hour or even several days, right? Depends on what kind of hardware you have. So now the idea is that whether we can design some benchmarks which is fast, but can capture some kind of essential communication patterns in the current existing deep learning benchmarks as well, so that we can use such minutes or seconds to get your numbers and get the benefit reports, something like that. So that's why we designed a micro benchmark with gRPC based on the profiling results I mentioned earlier. We are trying to generate those kind of patterns based on what kind of messages patterns, message sizes, and how many workers, how many primary servers we are able to generate a framework to benchmark your communication runtime design. With this, let me show you some of the numbers we got with our approach or our designs. So this is the comparison between our AR-GRPC and the default gRPC. This running with FDR InfiniBand. So as we can see that no matter small messages or medium messages or large messages, our design is able to show very good performance compared with the default gRPC runtime. The reason, like I said, we have been optimizing the runtime for both small one, medium one, and the large one. Then we adaptively choose the best path for each of these message size. For instance, for small one, we can achieve like a 2.7x speed up, and for medium one, 2.8x, and then for large one, 2.5x. We have a paper in HPC last year, so if you have interest about the details of design, please take a look. That's for the messages, the standard message size comparison for latency, right? And then, like I said, if we can use our benchmark to generate different kind of patterns. So you can generate the unified patterns, you can generate random patterns, you can generate skewed patterns. Then in that case, we want to see whether our design can adaptively get the benefit for different kind of patterns as well. So actually, this is taken from our benchmarks. If you look at these numbers, we can see that we can easily get these numbers within 1 second. But if you run ImageNet with some model, you may get 1 day to get those numbers, right? So this benchmark will help you to significantly reduce the time of your benchmarking or experiment. So here we compare with our AR-GRPC design with default gRPC running with 40 gig Ethernet or IP over IP with 100 gig per second performance. We will see that no matter unified, random, or skewed, we run our experiment on 2 different kind of clusters. One is our local cluster with EDR InfiniBand, and then one is SDC comment with FDR InfiniBand. So we're able to see that AR-GRPC is able to reduce around almost 60% latency for different kind of patterns. Okay, on this cluster, their IPLB performance is a little bit bad, so that's why we're able to see around 80% latency reduction. So this is about the throughput. Again, the benchmark what I mentioned earlier, we're able to measure your throughput as well. So throughput is important for primary server, especially, right? Because you may have a lot of workers, but all these workers are communicated with one primary server. So throughput is that's why throughput is very important for the primary server approach. So we measure this performance. We compare it with default gRPC running over 40 gig and also IP over IP. No matter what kind of patterns, we see a big performance improvement, almost more than 3x to 4x performance speed up for different kind of communication patterns. Now the next one is we're also trying to mimic TensorFlow communication like a graph, because by default TensorFlow communication graph is like a many-to-many. You have many primary servers with many workers, and then each of them will get connected like a full connected architecture, and then they're trying to send the gRPC requests concurrently, right? Some guys send some random pattern, some guys send them skewed pattern, and then everything happens concurrently. So we are using our benchmark to mimic TensorFlow communication exactly, and then we are trying to see that whether our performance will still be good. And especially here, we are trying to show large message because in for many deep learning training process, you will see that a lot of messages are actually very big, at least more than megabytes, okay, several megabytes. That's why here we show 2 megabytes, 4 megabytes, and 8 megabytes. So with our design, we are able to reduce latency around 60%, and then improve the throughput around almost 3x or 2.5x, something like that. So those are for the benchmarks we designed. Now let's take a look whether this kind of benefit still there if you run some real models with real data sets or benchmark data sets, right? So we start with GOOGLENET and ALEXNET. Here, interesting thing we can see is that we evaluated GOOGLENET and ALEXNET on the InfiniBand EDR cluster. And then because GOOGLENET only has around 5 million parameters, a little bit small relatively, okay? But ALEXNET has almost 60 million parameters. You have more parameters, basically means you need more communication, okay? So I remember there's a good survey that how many parameters being exchanged for different models. They are using some different kind of cycles to represent that. Bigger cycle means you have more communication requirements. And that's good for our community if you choose those kind of models, right? So as we can see, that's why you will see if you look at GOOGLENET and ALEXNET, where our design can give you much better performance than benefit than GOOGLENET. This is the reason, because you need more communication, right? So this shows you that AR-GRPC are almost 89% performance improvement for ALEXNET compared with default gRPC in these graphs. This is 8 nodes, this is 12 nodes. Okay, so Inception v4. Inception v4, I remember this is almost one of the most accurate model for DN training. So then here we compare with gRPC plus verbs, gRPC plus MPI, and with our AR-GRPC design. So as you can see that for 4 nodes, 8 nodes, 12 nodes, no matter what scale, our design are able to outperform other designs very well. For instance, we compare with verbs channel, because gRPC plus a dedicated verbs engine, okay? We are able to achieve around 27% or 12% or 31%, depends on different kind of scale and test. And then compared with MPI, we are able to show around 29%, 151, and 228 performance improvement. Here, I want to highlight that the default gRPC plus MPI design in the TensorFlow is not designed very well. That's why people trying to use hollow world MPI-based approach, or reduced-based approach for distributed neural network training. Because it seems like MPI is not, at least that channel is not designed well for primary server-based approach. And then ResNet 150 of ResNet, the version of ResNet. So again, we compared with different versions from 4 nodes to 12 nodes, and each node has 2 GPUs. So we also see similar kind of performance improvement. For instance, compared with default gRPC, we almost see like more than 60% improvement. And then compared with verbs, also more than 30% or 40%. And then compared with MPI, there's also 1.6, 3.3, or 4.5x speed up. We actually also evaluated with different kind of other different kind of DN models as well. So this is just summary. So compared with default gRPC, the speed up from I think it is 1.8 to 3x speed up. So we are trying to make this design available under the HiDL project. This is a new project, high-performance deep learning. Earlier I mentioned high-performance big data. That was for Hadoop, Spark, memory cache, or HBase, Kafka, those things. Now we have started a new project called HiDL, which we are trying to make some advanced designs for deep learning frameworks, including TensorFlow and the Caffe. So here we have the RDMA-based design for TensorFlow. You can download our package from here, this link, and then try it. So with this, let me conclude my talk. So overall, what I presented here is that I just want to share a story how you can utilize RDMA or high-performance networks to optimize TensorFlow-like distributed deep learning frameworks. So we give our view of what kind of designs internally or outside for TensorFlow as well as gRPC. And then we discuss kind of challenges of how to accelerate as well as how to benchmark it. So we believe that with good designs, we should be able to achieve very good performance with RDMA protocols compared with default TCP/IP or other approaches. But we also find that if you want to make your design perform very well, you have to make your design adaptively or co-design with different kind of communication runtime as well as the architecture. For instance, primary server architecture and the reduced tree-based architecture, their design may be different. Okay. So with this, our design show very good performance. If you want to try, please feel free to download the package. If you have any questions, I'll be happy to answer those. Just send us an email. We will be get in touch with you. Thank you. If there's any questions, I can answer that. Otherwise, we can discuss offline. Yeah.
Just a quick small question about the RPC throughput you have shown. Is it correct that I captured that it's 2500s RPC?
Which one?
Where you showed how many RPC per second you can get.
Oh, here, okay. Which, there's a multiple graphs for that.
Yeah.
Here, right?
So what's the main contributor to that RPC per second value? Because if you get that good latency, is it some kind of a for whole pattern?
No. That's why I mentioned, right? Latency is just only one metric. But if you look from parameter server approach perspective, the parameter server has to deliver very high throughput as well, because a lot of clients trying to communicate with me, right? If I'm a parameter server. So I have to guarantee that I'm able to respond a lot of gRPC cores concurrently. So that's why we want to measure the throughput.
I maybe just don't understand what benchmark they're doing, yeah. Okay. So it's a 2500s.
Yeah, but this is large message. Think about this is not like it's more like 1 bytes, 2 bytes. This I remember this. I don't exactly have to remember what's the message. This large message basically, because I mentioned. For deep learning, a lot of messages are actually more than megabytes, more than 7 megabytes. That's why you'll see only around thousands of cores per second. But if you reduce the message, definitely you can go to very big numbers. Any other questions? Okay. If not, thank you.